Hi everybody. Now, what is flux? This is already known to us. Now, as we were discussing last class, we need to correlate or first identify what are the variables associated with this diffusion process and how can we correlate those variables so that we can ultimately reach through some mathematical equations so that we can calculate quantitatively the amount of diffusion for a particular case where the other terms are identified and known to us. Now, before we take any problem under consideration, we should be knowing how this mathematical equation can be developed. So, as we have already discussed, G, which is nothing but diffusional flux, is nothing but atoms per area per time or mass per unit area per time, and which is the actual quantity of that particular material diffusing through the perpendicular area, as we have already discussed in the last class. So, this is J, already we have discussed. So J is proportional, as in the introductory classes we discussed. Like other operations, diffusion is also dependent on the driving force. So amount of diffusion will be dependent on the driving force, which is nothing but the concentration gradient, or precisely the chemical potential difference. If we consider a single phase, then concentration gradient is the driving force. Therefore, the amount of material diffusing through a perpendicular area must be proportional to the driving force, that is concentration gradient. So in terms of differential manner, the concentration gradient this time is nothing but the concentration difference across the distance through which diffusion is taking place, and this distance must be measured as the perpendicular distance to the direction of the flow of diffusion. So recall the picture of metal slab which had two surfaces, one upstream surface, that is point A, another downstream surface, that is point B. So these two surfaces are separated by the distance, that is the thickness of the slab, which is nothing but the dx. So infinitesimal distance across which the concentration difference dc exists, that is dx. Therefore, the concentration gradient must be dc by dx. In finite manner, this must be c2 minus c1 divided by x2 minus x1. As the concentration decreases down the direction of the flow, so dc must be always negative. That means c2 minus c1 must be negative. So that is why if we put the equal sign introducing a constant, J must be equal to minus into some proportionality constant, which is expressed here as capital D into dc by dx. Now as we know, capital G or flux is nothing but dN by dt, where n is the number of atoms. So number of atoms crossing the perpendicular area A, as we have discussed in the early class citing a picture of metal slab. So surface area was capital A. So 1 by A dN dt is the flux again. Already we defined J equal to 1 by A dN dt. So dN is the number of moles crossing through the perpendicular area A within the range of time dt. So 1 by A dN dt must be flux J, that is equal to minus capital D into dc by dx. Therefore dN by dt, that is number of atoms crossing area per unit time. So this thing is nothing but dN dt. So dN dt must be equal to minus d, minus sign is for because the concentration decreases as we follow the direction of flow. D is the proportionality constant, A is the total area through which perpendicular area rather through which diffusion is taking place. dc is the concentration difference across the wall or across the thickness or across the distance dx. So dc by dx is the concentration gradient. So total equation comes like dN by dt equal to minus capital T into capital A into dc by dx. Now this d term is called as diffusional coefficient, or simply which is popularly known as diffusivity. So this is known to us, capital D is the diffusivity. So this equation dN dt equal to minus dA dc by dx is popularly known as Fick's first law. I think some of you have already heard this particular equation. This is the famous Fick's first law for molecular diffusion. Thank you. We will be now forwarding to apply this particular equation for solving numerical problems and other diffusional application problems. Thank you.